The James Webb Space Telescope stands as the premier global observatory in the field of space science, embarking on a mission to investigate the enigmas surrounding our own solar system, distant worlds orbiting remote stars, and the complex structures of the universe, while exploring humanity's role within it. In a recent groundbreaking initiative, scientists directed Webb toward a star located 120 light-years away from our solar system, revealing compelling evidence for the existence of carbon-based molecules in the atmosphere of a possible ocean world. This revelation has sent shock waves through the astronomical community, offering an unprecedented glimpse into a planet significantly different from any within our solar system, and raising profound questions about the possibility of habitable worlds in other corners of the vast universe. The James Webb Space Telescope has made a particularly relevant discovery regarding the exoplanet K2-18b, which possesses a mass approximately 8.6 times that of Earth. This finding is centered on the identification of carbon compounds, including methane and carbon dioxide, within the planet's atmosphere. Webb's discovery adds a new layer to previous research, which suggested that K2-18b could be a Hycean world, a planet with a hydrogen-rich atmosphere and a vast ocean-covered surface. The first exploration of this exoplanet's atmospheric properties was conducted using NASA's Hubble Space Telescope, which fundamentally transformed our understanding of the system. Located in the constellation Leo, K2-18b orbits a cool dwarf star known as K2-18, which resides in the habitable zone of its solar system, a region where conditions may be favorable for liquid water to exist. Exoplanets like K2-18b, which fall between the size of Earth and Neptune, are a rare category within our solar system, making them particularly intriguing targets for scientific exploration. Due to the absence of such planets in our immediate cosmic neighborhood, the study of these sub-Neptunes is crucial in expanding our understanding of planetary formation and the potential for life beyond Earth. The possibility that K2-18b is an exoplanet with a significant abundance of carbon compounds and a hydrogen-rich atmosphere is particularly intriguing to astronomers, as many experts believe that such worlds could offer ideal conditions for the search for extraterrestrial life. The presence of methane and carbon dioxide, coupled with the absence of ammonia, supports the theory that K2-18b might harbor an ocean beneath its hydrogen-rich atmosphere. Early observations of this exoplanet also hinted at the potential detection of dimethyl sulfide, a compound that on Earth is exclusively produced by biological activity, primarily by phytoplankton in marine environments. However, the evidence supporting the presence of dimethyl sulfide on K2-18b remains inconclusive and requires further confirmation. Future observations utilizing an extensive telescope network will aim to verify whether this compound exists in significant quantities within K2-18b's atmosphere. An astronomer at the University of Cambridge emphasized that while K2-18b's placement within the habitable zone and its carbon-rich atmosphere are compelling, they do not automatically imply that the planet is capable of supporting life. With a radius approximately 2.6 times that of Earth, K2-18b likely possesses a dense core surrounded by an immense high-pressure mantle composed largely of ice, similar to the internal composition of Neptune. This, combined with its thinner hydrogen-rich atmosphere and ocean-covered surface, suggests that while liquid water may be present, the planet's environmental conditions may still be too extreme or unsuitable for sustaining life as we know it. However, researchers have now obtained the most detailed spectrum to date of a habitable sub-Neptune, allowing them to identify the specific molecular components within its atmosphere with unprecedented precision. The challenge of studying K2-18b's atmospheric composition was met by analyzing the light emitted by its host star as it passed through the exoplanet's atmosphere. As a transiting exoplanet, K2-18b periodically moves in front of its star, causing a temporary dimming of the star's brightness. NASA's K2 mission was able to detect the exoplanet using this method, which also enabled astronomers to examine how a fraction of the star's light interacted with the molecules in the planet's atmosphere. The specific absorption and scattering patterns in this light provided key insights into the atmospheric gases present. Moving forward, scientists plan to conduct additional investigations using the telescope's mid-infrared spectroscopy, which will confirm their current findings and provide further information about the climatic conditions on K218b. Their ultimate goal remains the search for signs of life on habitable exoplanets, a breakthrough that could fundamentally redefine our understanding of the universe. Beyond the study of exoplanets, the James Webb Space Telescope has also uncovered other extraordinary findings, including the detection of complex organic molecules in a distant galaxy. These molecules, akin to those found in smoke or smog on Earth, represent the earliest known example of complex carbon-based compounds ever identified in the universe. This discovery has profound implications for cosmology and planetary science, challenging long-held assumptions about the timeline of molecular formation in the early universe. The chemicals detected, technically referred to as polycyclic aromatic hydrocarbons, were found in a galaxy that existed when the universe was only about 10% of its current age. On Earth, these molecules are commonly associated with fossil fuels and atmospheric pollutants, but their presence in an ancient galaxy suggests that complex organic chemistry was occurring much earlier than previously thought. What makes this discovery particularly significant is that the molecules detected are not simple structures like water or carbon dioxide, but rather large, complex hydrocarbons composed of dozens or even hundreds of atoms. The rapid emergence of such sophisticated molecular structures so soon after the Big Bang defies conventional expectations based on existing cosmological models. To put this into perspective, the light that astronomers detected from this early galaxy, known as SP4-11847, began its journey less than 1.5 billion years after the Big Bang. Given that the universe is approximately 13.8 billion years old, this means that we are essentially observing some of the earliest chemical processes that shaped the cosmos as we know it today. What is perhaps most remarkable about this detection is that it was only made possible by the unparalleled capabilities of the James Webb Space Telescope. With its advanced instruments and extraordinary sensitivity, Webb has the potential to continue making such groundbreaking observations for nearly a billion more years. Raises the question: if we were to peer even further back in time, might we uncover more of these complex molecules, perhaps even closer to the Big Bang itself? Such a discovery would fundamentally reshape our understanding of the origins of chemical complexity in the universe. Until now, previous efforts to detect complex organic molecules in ancient galaxies were limited in their ability to determine the exact location and distribution of these compounds. However, Webb's ability to provide higher resolution data has now allowed astronomers to map the spatial distribution of these molecules with remarkable precision. Interestingly, the presence of these molecules within SP4-11847 is not uniform, a phenomenon that has yet to be fully explained. Adding to the intrigue is the fact that, despite being only 1/10 the age of the Milky Way, this galaxy already possessed a mass comparable to our own and had generated significant amounts of carbon and oxygen, key elements necessary for life as we understand it. As humanity ventures deeper into the unknown, armed with advanced technology and a relentless curiosity, we are continuously humbled by the vastness and complexity of the cosmos. Each new discovery serves as a reminder of how little we truly understand about the universe and our place within it. With each scientific breakthrough, we take another step closer to unraveling the mysteries hidden among the stars. As our cosmic exploration network expands, it is only a matter of time before the universe unveils even more of its long-held secrets, shining with renewed brilliance and challenging everything we thought we knew. The discoveries made by the James Webb Space Telescope, JWST, extend beyond individual exoplanets and galaxies, reshaping our fundamental understanding of planetary systems, cosmic evolution, and even the origins of life. One of the telescope's greatest contributions is its ability to observe the atmospheres of exoplanets in unprecedented detail, bringing us closer to answering one of humanity's most profound questions: are we alone in the universe? The detection of methane and carbon dioxide in the atmosphere of K218b, along with the potential presence of dimethyl sulfide, marks a significant step forward in astrobiology. If further studies confirm the existence of this molecule, it would suggest that biological processes are taking place on a world over 120 light-years away. However, scientists remain cautious, as abiotic processes can sometimes mimic biological signatures, making it essential to rule out non-biological sources before claiming evidence of extraterrestrial life. To ensure a thorough investigation, astronomers plan to conduct follow-up observations using Webb's mid-infrared instrument, MIRI, which will allow them to analyze the thermal properties of K2-18b and its atmospheric composition with even greater precision. If the planet does indeed have a global ocean beneath a hydrogen-rich atmosphere, it would challenge traditional models of planetary habitability. Until now, the search for life has largely focused on Earth-like planets with nitrogen-oxygen atmospheres similar to our own. However, the discovery of a potentially habitable Hycean world suggests that life could exist in a much wider range of environments than previously believed. This expands the scope of astrobiology, prompting scientists to rethink their criteria for habitability and broadening the list of exoplanets that merit further study. The implications of Webb's findings are vast, not only for exoplanet research, but also for our understanding of planetary formation and evolution. For instance, planets like K2-18b challenge conventional planetary classification systems. In our solar system, planets are typically grouped into terrestrial planets like Earth and Mars and gas giants like Jupiter and Saturn. Subneptunes, however, represent a unique category, occupying an intermediate space between rocky planets and gas giants. Their atmospheres, surface conditions, and internal structures remain poorly understood, making Webb's ability to study them in detail a game-changer. By analyzing how light interacts with K2-18b's atmosphere, scientists can infer the planet's chemical composition, temperature, and even potential weather patterns, offering an unparalleled glimpse into an entirely new class of worlds. Beyond exoplanetary science, Webb's recent discovery of complex organic molecules in an ancient galaxy has profound implications for our understanding of cosmic chemistry and the early universe. The presence of polycyclic aromatic hydrocarbons, PAHs, in a galaxy that existed when the universe was just 1.5 billion years old suggests that complex carbon chemistry emerged much earlier than expected. These molecules, which are found in fossil fuels and atmospheric pollutants on Earth, are thought to play a crucial role in the formation of life. Their detection in the early universe raises intriguing questions about the conditions that may have led to the development of life elsewhere in the cosmos. Traditionally, astronomers assumed that the early universe was dominated by simple molecules such as hydrogen, helium, and basic compounds like water and carbon monoxide. The discovery of large, complex organic molecules at such an early stage in cosmic history challenges these assumptions. It suggests that the chemical building blocks of life were widespread throughout the cosmos long before Earth even formed. This finding also aligns with the hypothesis that the raw materials for life could have been delivered to planets via interstellar dust and comets, a process that may have played a role in Earth's own origins. What makes this discovery even more remarkable is the non-uniform distribution of these molecules within the galaxy SP 4-1-1847. Unlike previous studies, which could only confirm the presence of organic molecules without identifying their exact locations, Webb's advanced spectroscopic capabilities have revealed that these compounds are concentrated in specific regions. This raises important questions about the physical and chemical processes that govern the formation of complex molecules in space. Are these regions more conducive to molecular assembly due to the presence of certain stellar populations? Could intense ultraviolet radiation from young stars be playing a role in shaping these molecules? Understanding these dynamics will provide critical insights into the chemical evolution of galaxies and the factors that determine whether planetary systems develop the necessary ingredients for life. Webb's ability to peer into the past, capturing light that has traveled for billions of years, provides an unprecedented opportunity to study the universe's earliest epochs. The discovery that galaxies like SP 4-1-1847 had already accumulated significant amounts of carbon and oxygen just 1.5 billion years after the Big Bang suggests that star formation and chemical enrichment occurred much faster than previously thought. This could mean that the first habitable worlds formed earlier than expected, increasing the likelihood that life may have emerged elsewhere in the universe long before Earth came into existence. As we continue to push the boundaries of space exploration, each new discovery serves as a testament to humanity's insatiable curiosity and relentless pursuit of knowledge. The James Webb Space Telescope, with its unmatched sensitivity and resolution, is not only answering long-standing questions, but also raising new ones that challenge our understanding of the cosmos. What other secrets lie hidden in the depths of space, waiting to be uncovered? Could the next breakthrough bring us face-to-face with undeniable evidence of extraterrestrial life?